Hello friends, good morning. In the unit on circuit breaker, till now I have explained what is circuit breaker, how it works, arcing phenomena, details of arc voltage and arcing phenomena, and in my last video lecture I had explained different terms associated with the circuit breaker. The first term was recovery voltage. Definition is, it is the normal frequency voltage which appears across the breaker poles at the instant of arc interruption. Second term was active recovery voltage. It is nothing but the instantaneous value of the recovery voltage at the instant of arc interruption. Then we had derived the expression for active recovery voltage. Third term is restriking voltage. It is the transient voltage which appears across the breaker poles at the instant of arc interruption. This is also called as transient recovery voltage. In this video lecture, I will explain all the details of restriking voltage. We start with the derivation for the restriking voltage. That is, we derive the expression for the restriking voltage. So let us start with this definition. Restriking voltage, we denote this by V suffix RS. It is the transient voltage which appears across the breaker poles at the instant of arc interruption. So to derive the expression, we take this single line diagram. Generator, there can be transformer, then circuit breaker, and connected to the transmission line, it is going to other bus. We assume that fault takes place just after the circuit breaker. Fault takes place just after the circuit breaker. Fault can take place anywhere in the system, but for derivation, we are assuming that fault takes place just after the circuit breaker because this condition is severe when fault is near to the circuit breaker or the source, because in that case, current is maximum. Now we start with three basic assumptions for derivation. Assumption number 1, resistance of the circuit is neglected. That is assumption number 1. Assumption number 2, inductance of the circuit is lumped at one point. Meaning is, this generator is having some inductance, then if there is transformer, that will also have some inductance. So we are clubbing these inductances, all the inductances of the system up to the fault point, and we are denoting this by. Third assumption is, we are considering only the capacitance of circuit breaker pushing, and it is here. There can be other capacitances also, that is of generator winding, transformer winding, then transmission line. But at present, we assume that we are assuming only, or we are considering only the capacitance of circuit breaker porcelain bushing. So this will be the equivalent circuit: source, then inductance up to the circuit breaker, then this is the capacitance of circuit breaker porcelain bushing, and this is circuit breaker. This is fault point that is shown here. So let us start. When fault takes place, current is flowing to this fault through the circuit breaker. Then circuit breaker operates, relay detects the fault, relay closes its contact, trip coil of the circuit breaker is energized, and circuit breaker contacts start separating. When they are separating, there is an arc between the contacts, and finally the arc interruption takes place. So when arc interruption takes place, this fault current is removed. When arc interruption takes place, we have restriking voltage across the circuit breaker poles. Now this restriking voltage is transient in nature. So there will be high frequency transients. So we have to find the natural frequency of oscillation of this voltage. So Fn is natural frequency of oscillation of this voltage, and that is 1 upon 2 pi under root LC, L and C. Let us say equation number 1. So this transient voltage or this high voltage oscillates with this natural frequency given by 1 upon 2 pi under root LC. Now when current starts flowing to this fault, current will start flowing through this circuit breaker porcelain bushing, that is IT. So this path or this loop will form a closed circuit. So we can say VT. Now at the instant of arc interruption, this VT is nothing but active recovery voltage. So VT is nothing but active recovery voltage, that is L di by dt plus 1 by C integration IT dt. Say equation number 2. So this is the current flowing, this is the equation for the current flowing through this circuit, and this is equation for natural frequency of oscillation. Say equation number 2. Now transient voltage which is appearing across the breaker poles will be given by, will be nothing but the voltage which is appearing across this capacitance, that is capacitance of the circuit breaker porcelain bushing, and this voltage is nothing but this one. that is 1 by c integration it dt, that is equation number 3. So with these three basic equations, I am not going into details of derivation. I will directly write the equation for restriking voltage by solving this equation. This is a differential equation. We take, it is first order differential equation, so we take the derivative of this. So when we take the derivative, this component will become 0. This will become L d2i by dt square 1 by c integration. This will vanish and this will be 1 by c it dt, 1 by c it. Then we solve this equation for getting it, equation for it. We apply the initial conditions, and after getting the equation for it, we substitute this here, and then we integrate with limit, and after proper substitution applying initial conditions, we get the final equation for the restriking voltage. Now I will directly write the expression for the restriking voltage. So after appropriate substitutions and simplification, we get the expression for restriking voltage VRST, because it is the function of time. So it is active recovery voltage multiplied by 1 minus cos omega t. This is the equation. Now omega is nothing but 2 pi Fn. So omega can be replaced by 2 pi Fn. So this equation is active recovery voltage multiplied by 1 minus cos 2 pi Fn t. Now equation number 1 was for natural frequency of oscillations, that is 1 upon 2 pi under root LC. So if we replace Fn by 1 upon 2 pi under root LC, we get this equation for the restriking voltage, active recovery voltage into 1 minus cos t upon under root LC. So these three are the expressions for restriking voltage. Say equation number 4. Now when we consider any of this equation and plot the restriking voltage as a function of time, we find that it is sinusoidally varying with natural frequency of oscillation Fn is equal to 1 upon 2 pi under root LC, and it is unidirectional. So it is varying between 0 and peak value. 0 and peak value it is varying, because when omega t is, when t is 0, this will be 1. So restriking voltage will be 0. And to find the maximum value of this restriking voltage, we have to substitute, we have to take this part is equal to minus 1. So when cos of 2 pi Fn t is minus 1, this will be minus 1, minus 1, 1 plus 1, 2. So active recovery voltage, the maximum value of restriking voltage will be 2 times active recovery voltage, and this happens when 2 pi Fn t is equal to pi, because cos of pi is minus 1. So 2 pi Fn t is equal to pi means t is 1 upon 2 Fn. Now Fn is 1 upon t, so it is t by 2. So this is complete time period. So at t by 2, this restriking voltage will be maximum. So this is the expression for restriking voltage. This is the maximum value attained by restriking voltage, that is 2 times active recovery voltage, and this is the time at which this restriking voltage is maximum. This we have derived by substituting cos of 2 pi Fn t is equal to minus 1, that is 2 pi Fn t is equal to pi. So this is the expression for restriking voltage, and this is maximum value of restriking voltage, and this is the time at which it is maximum. Now the severity of this restriking voltage, that is how much it is affecting the system, circuit breaker insulation, etc., not only depends on the peak value of this restriking voltage, but also rate of rise of this restriking voltage. So here we introduce one important term, that is RRRV, rate of rise of restriking voltage, RRRV. So we derive now the expression for RRRV, and two terms will be there. One is average RRRV and second maximum RRRV, and we have to find the time at which this RRRV is maximum. So let us find the equation for RRRV average and RRRV maximum. So this is the waveform for this restriking voltage. Along x-axis we are taking time, along y-axis we are taking the magnitude of VRST. This is varying like this, unidirectional. So this is the peak value, that is maximum restriking voltage, and it occurs at time t by 2 because this is total time period. So RRRV is obtained by slope of this. So for slope we apply the condition y2 minus y1 upon x2 minus x1. So y2 is BRS maximum minus y1, that is 0, x2 t by 2 minus 0. So this is the expression for average RRRV. We are assuming that this increase is linear. This increase is linear, and we are applying the slope condition to this linearity. So VRS maximum is nothing but 2 times active recovery voltage. T by 2 is nothing but Fn. T is 1 upon Fn. So it is 2 times Fn. So total, so equation is 4 Fn active recovery voltage, and it is expressed in kV per microsecond, because for plotting the striking voltage we are taking time in microseconds and magnitude we are taking in kV. So the equation, the RRRV obtained is in kV per microsecond. Let us say it is equation number 6. So when we don't mention anything with this RRRV, we have to assume that it is average RRRV. Now RRRV maximum. So for this we assume that it is varying according to this equation, and we have to apply the condition for maxima, or we have to find the maximum slope of this equation. So when we apply the condition of maxima to this expression for restriking voltage and equate this to 0, we get maximum RRRV is 2 pi Fn active recovery voltage, and time at which it is occurring is 1 upon 4 Fn. Means at this time, that is at t by 4, it is maximum. So maximum RRRV occurs at time t by 4. Capital T is the time period, and maximum RRRV is 2 pi Fn into active recovery voltage. So let us say this equation is equation number 7. So this maximum RRRV will also be expressed in kV per microsecond. Now let us find out what are the factors on which this restriking voltage depends on. So from this equation it is obvious that it depends on active recovery voltage, and active recovery voltage depends on 3 factors, that is power factor of the system, demagnetizing effect of armature reaction, and third, circuit condition. So circuit condition factor will be 1 for earth fault, and it is 1.5 for ungrounded system. So it depends on active recovery voltage, and it depends on the natural frequency of oscillation, that is on inductance of the circuit and capacitance of the circuit. So these are the factors which affect the magnitude of restriking voltage. Now let us see what are the factors which affect the magnitude of RRRV and maximum RRRV. So here we get it is Fn and active recovery voltage. So again same factors, that is for active recovery voltage it is power factor of the circuit, demagnetizing effect of armature reaction, and circuit factor, that is circuit condition. And for Fn it is L and C. So whatever factors which are affecting the restriking voltage magnitude, they are affecting the maximum value of the restriking voltage as well as RRRV and maximum RRRV. So this is all about restriking voltage, RRRV and maximum RRRV, and the time at which the RRRV is maximum, and at the time at which the striking voltage is maximum. Now in the beginning we had defined 3 assumptions. Now let us see what happens when we violate these assumptions. Our first assumption was resistance is neglected. Now when we consider the resistance, we violate the first assumption. The restriking voltage waveform will be like this. Obviously we are taking time along x-axis in microseconds and magnitude of restriking voltage along y-axis in kV. Now this resistance, if it is not equal to 0, it will provide damping. So progressively the amplitude of this restriking voltage waveform will go on reducing because resistance is providing the damping. So we are violating the first assumption and getting this type of voltage, this type of waveform for the restriking voltage. Now if we are violating first, second and third assumption, first is resistance is not equal to 0. Second, there can be more, we are not lumping the inductances, means inductances will be separate. Let us assume that at two different points inductances are there and at two different points capacitances are there. So two different frequencies of oscillations will be there. One may be providing oscillatory nature and second may be providing the critical value, critical or overdamped response. So if one is providing underdamped response, then this will be the restriking voltage waveform due to first frequency. Suppose second is providing overdamped or critically damped waveform, then this is the restriking voltage due to second frequency. So one LC is giving this type of waveform, second LC is giving this type of waveform. So when we have to find the resultant of these two, we have to superimpose this waveform on this. So this will be the resultant restriking voltage waveform. So this is how we are getting the restriking voltage waveforms when we are violating the assumptions. So in this video lecture, I have covered restriking voltage, RRRV and RRRV maximum, and the time equations for the time at which restriking voltage is maximum and RRRV is maximum. I also explained the factors which affect the magnitude of restriking voltage as well as RRRV. Friends, if you feel this video lecture useful, then please like it, subscribe to my channel, ask your friends, colleagues and juniors to subscribe to my channel for video lectures on high voltage engineering and power system protection. If you want to make effective and efficient use of time, then read my book on time management. The link for the book is given in the description box. I have launched a useful course for the students on UDEMY. This course is very useful for the students who are preparing for the competitive and entrance exams. The link for the course is also given in the description box. Thank you.